I decided to walk you through slowly, step by step, because now you have background coming in. This is what we're intending to accomplish in this section. And if you think back, it's always been pretty hard to understand where it is things are coming from. Let's trace them back. Again, in chapter 4, you learned that solubility is governed by the anion of the salt. You learned that there were many ionic compounds that were always soluble. Yes, there were exceptions. You also learned that there were compounds that were insoluble, and it was all based on the anion. Now you are learning that these insoluble compounds have a KSP. We didn't tell you that back in Chemist 1210. So there are some facts as we get started. If we take calcium fluoride, we can only dissolve 16 milligrams in a full liter of water. That is called the solubility of calcium fluoride in water. You talk about a solubility in grams per liter, but you can also talk of a solubility in moles per liter, and that is the concept of molarity that you are interested in. So we have 16 milligrams of calcium fluoride. We know its molecular weight, so we get rid of the grams, and we know that here we have the number of moles, here we have the number of liters. There is our molar solubility. Contrast this to sodium chloride. Sodium chloride, I could put 350 grams in a liter of water. I can't do that with calcium fluoride, so that has KSP. So what is this KSP? Well, it's another version of an equilibrium constant, products divided by reactants. And I think the best way to understand it is to listen to how the experiments were done. Solid sodium chloride was placed in water and vigorously stirred. They let this stir for days. Not something you can do in the lab. It's something that is done where we have time to do it. That's why they call them careful experiments. They showed that small amounts, very small amounts of silver chloride actually dissolved in water. The silver chloride that dissolves, it completely dissociated into ions. Now you understand this because you've been in 1210. So it makes sense that a solid can dissolve into ions. Notice that it is an equilibrium. There is the double-headed arrow. And this equation has an equilibrium constant expression. And what we have again is products divided by reactants. Here are the products, silver cation, chloride anion. In terms of the reactants, we never put solids into the equilibrium expression. When people measured this, they found a number 10 to the minus 10. That is much, much less than 1. That means our eye isn't really going to be able to see those ions in solution, but they are there. Note this is a heterogeneous equilibrium because we have both solids and aqueous, and the product is always, always, always the product of the molar constituent ions. And just like it was in the past, they're raised to a power that corresponds to the number of ions in one formula unit. So my last slide in this section, there isn't much if you take your time and go through it slowly. Here is my calcium phosphate. You learned how to write these equations in 12.2.10. 1210, where you had to use the stoichiometric coefficients to describe the number of ions. All we're doing here is translating this into an expression for equilibrium, which we learned back in chapter 15. So that is for an actual calcium phosphate, but we can generalize for any metal and non-metal ionic complex. You can make that statement. So you can have a real life ionic solid, or you can have one of the conceptual solids. Here's the take-home words we need to learn. Solubility, that's measured in grams per liter, and that's the quantity that can dissolve in a solvent. We tend to work in water in chemistry 1220. Molar solubility, well, that's where I've changed those grams into moles. Again, something you learned back in chemistry 1210. And just to reinforce, KSP has no dimensions. Remember, you have had already 4 different Ks, KC, KP, Ka, Kb. All of them were dimensionless.